So far as chemists, you've realized that weighing things out is very important. And there also can be times when having a sense of how many atoms or molecules you're working with can also be important. So chemists have a unit called the mole that they use, and that mole is going to allow them to have a sense of how many particles they're working with. So down here is the definition of what a mole represents. A mole is the number of atoms in exactly 12 grams of carbon-12. So that seems really vague, but let's draw it out and get a sense for what that means. In the periodic table, you learned carbon has an average mass of 12.01 AMU, atomic mass units, and this number is based on averaging the different carbon isotopes based on their masses and relative abundances. Now, we know that the most abundant carbon is carbon-12 isotope. So let's picture we had a pile of carbon-12 atoms, such that 12 grams of carbon-12 were weighed out. Well, if we had exactly 12 grams of carbon-12, which is what carbon weighs in atomic mass units, then however many particles it takes to get that 12 grams, that's what we define as 1 mole. So how many particles is that? Well, particles are really small, so many experiments were done later to determine this number. This turns out to be how many atoms of carbon-12 there are in 12 grams of carbon-12. And this number is humongous, so just imagine writing 6.022 with moving the decimal place 23 spaces to the right. It's a very large number. This number is called Avogadro's number, and it's named in honor of Avogadro, who didn't really come up with this number at all. This number came up many years after he died. But he was instrumental as someone who gave us an idea about particles and the amount of space they took up and what that has to do with the number of particles we have. So when you study gases, you may learn more about that. So the mole can be used for any objects. Now, for particles, this number is appropriate for very small objects. So for particles, we mean atoms, molecules, formula units, etc. Now, let's talk about some of these terms. So an example would be if we pick iron, for example, we have 1 mole of iron. Then iron exists in atomic form, so Fe atoms. So 1 mole of iron would be Avogadro's number of iron atoms. What if we're talking about 1 mole of hydrogen? Well, hydrogen is one of those Brinkelhoff elements, so it occurs diatomically. So H2, which is a molecule, so a molecule is, in this case, 2 atoms bonded together. So because it's 1 mole of anything is Avogadro's number of those things. So it's this many things, but those things are H2, and H2 is called a molecule. So these are molecules. And sorry, that's a 2. All right, and then let's say we have something else like an ionic compound, 1 mole of NaCl. So that's Avogadro's number of NaCl. But NaCl is not an atom and it's not a molecule. It is an ionic compound. So ionic compounds are called formula units. So there's one formula unit is the simplest unit occurring in a sample of sodium chloride. So I'm going to put formula units here. So that's the name of this kind of particle for an ionic compound. All right, all atomic masses then can be taken from the periodic table, and they will be defined as the mass of 1 mole of that element. So for example, let's take carbon again. The molar mass will be 12.01 grams per mole. Hydrogen, 1.01 grams per mole. This is how many grams of that element is in 1 mole of that element. What if I wanted 1 mole of, trying to think, aluminum here, 26.98. So I just get these from the periodic table, But instead of atomic mass unit, or AMU, I'm talking about molar mass, which is grams of that substance per 1 mole of that substance. For compounds, I just add up the molar masses of their individual particles. So for example, H2, H is 2 H's, which is 2 times 1.01. So that's going to be 2.02. And then I also have an oxygen here. 1 oxygen is going to be 16.00. So I'm going to add those two together and I get 18.02. Now 1 water molecule is 18.02 AMU, but 1 mole of water, so a huge number of water, Avogadro's number of water, that's going to equal 18.02 grams per mole. All right, so if I wanted 1 mole of water, I just weigh out 18.02 grams. Now one note here, I'm using 2 decimal places for all of my molar masses because that's going to provide me with enough sig figs to do these problems without losing any precision. Okay, so 1 mole of anything, how is it related to the number of particles and the mass? It's basically just like what I did up here. 1 mole of carbon is 6.02 times 10 to the 23 particles. In this case, atoms of carbon. The mass is going to be 12.01 grams. All right, and so you can just fill out the table like that. And you'll notice 1 mole of anything is the same number. It's Avogadro's number of those particles. But the mass of that depends on what it says in the periodic table. Calculations now. The mole is really a central unit in connecting what we see and what we can feel and weigh, like grams, and the number of particles which we can't see or feel or have any sense of, right? So mass, we usually think of this in grams. And this is what I call the macroscopic world. This is what we can see. This is what we work with. This is where we live. Microscopic world are the things that we can't see. So I can't count individual particles, these really tiny things called atoms and molecules. So the mole is really central in connecting us from these two worlds to these two worlds. So we're going to do that by using 2 kinds of conversion factors. I think of the more important one, the more useful one is this one. We're usually going from grams to how many moles because we just need to know how many packets of things we have. We don't necessarily need to know exactly how many things we have. But there is a way to do this as well in case you're interested, and you'll see problems like this too. So going from mass to moles, well, we have this concept here of the molar mass, grams to moles. So anything with a conversion with both units is going to allow you to convert between them. So this here is the molar mass. So we'll have a way to connect, go back and forth using the molar mass here. For the mole to the number of particles, if we want to actually know how many particles we're working with, that has to do with this, right? Moles to particles and back and forth. So that's going to be Avogadro's number. All right, so let's take a look at some of these problems and identify how we're going to do the conversion. How much does 13.6 moles of a sample of copper weigh in grams? So here's the key. I'm looking at that and I'm looking at this. I'm starting with this and I want to go here. So moles to grams, that's from moles here to grams here. So I'm going to use that. So starting with 13.6 moles of copper, I'm going to set up a conversion and I'm going to end up with grams. So that means I need to use the molar mass. That's what's going to connect me. So molar mass of copper, look it up on a periodic table. But before you do that, just get used to using the units. Moles here goes down here. And that's to grams up here. And then look up your molar mass for copper, Cu, and then it says 63.55. So use 2 decimal places because you want to have at least enough digits to use to round properly at the end. And that goes with grams, not with moles. So it's 63.55 grams in 1 mole of copper. So now you know you can multiply those numbers and get the answer there. So let's try that. And then you want to round this to 3 sig figs because you're starting with 3. So I get 864. And let me just make sure real quick that I have the right molar mass for copper. There we go. Copper right here, 63.55. All right, good. Okay, the next problem. How many moles of CO2 molecules are in 0.25 grams of CO2? So we're starting with this number here, 0.25 grams of CO2. And what we want to find are how many moles of CO2. We don't want to know how many molecules of CO2 there are, even though it says CO2 molecules. It says how many moles of molecules do we have? So we want moles. So we're going from grams to moles. So we're going to start with 0.25 grams CO2. And then we want grams down here and moles up here. And this is going to give me moles of CO2. And what are CO2? They're molecules. So I'm asking for moles of these molecules. Or if you want, how many groupings of these molecules do I have? Where a grouping is this many. Okay, so a lot of times people call this the chemist's dozen, because a dozen is how bakers group things. And for us, that bigger number is more relevant because these particles are so small. Okay, find the molar mass for CO2. We're going to add up carbon, which is 12.01, times 16, or I'm sorry, plus 16 times 2, so that's 32 plus 12. So we're going to get 44, and I'm going to use 2 decimal places in that. And I'm going to set it up like this and see how those units cancel out. Now if you're really good, you'll include these little labels too. So 1 mole of CO2 over 44.01 grams of CO2. Then do your division here, 0.25 divided by 44.01. And I get 0.0056853. I'm going to round it to 2 sig figs because of this 0.25. So 0.0057. So here are my 2 sig figs right there. You can use scientific notation if you want, 5.7 times 10 to the minus 3. This is in moles of CO2 molecules. How many formula units? Now this is a type of particle for ionic compounds are in this many moles. So I'm going to start with moles, NaCl. I want to know how many particles there are. So these particles, because NaCl is ionic, it's called a formula unit. Formula units. Okay, so up here in this concept map, now I'm going from moles to particles. Particles can be atoms, molecules, formula units. All right, so atoms, molecules, formula units, I want to come over here, as long as they don't ask for moles of them. So what I want is the actual number of the formula units. So I'm going to say there's Avogadro's number of these particles in 1 mole of NaCl. So moles cancels out here, and I'm going to multiply these 2 numbers and then put that here. Now for this is sort of a nice thing in your calculator is to use an EXP button or an EE function if you have that. Usually it's above your, I think it's above, I can't remember, but I think it might be near your log button somewhere. So you've got EXP and EE. EE is what you would type in to mean times 10 to the 23. So for example, you could type 6.02 E or EXP 23, and that also means times 10 to the 23rd power. So it's a nice way to, a little shortcut. So 0.7 times that All right, so I get 4.214, but this only has one sig fig in it, so I'm just going to round it down to 4 times 10 to the 23. This is how many particles are in 0.7 moles. And that makes sense. 1 mole is 6 times 10 to the 23, so 0.7 moles is a little bit less than that, 70% of that. So this is NaCl formula units. Okay. All right, now let's take a look at down here. So identify, we're starting with this 63.9 grams of sucrose. How many moles of sucrose molecules? So we're going to moles. Okay, so grams to moles. Grams to moles, I just need to use the molar mass. Now the molar mass of this is pretty large. You got 12 carbons, 22 hydrogens, 11 oxygens. You got to add that all up. And I believe you'll get something like 342.34 grams per 1 mole. And again, if you're really good, you'll include what you're talking about. So I'm going to try to do that too. Set a good example. This pen's difficult. Okay, there we go. 63.9 divided by 342.34 is 0.817. And this is moles, because my grams canceled, of this C12 sucrose, C12H22O11. All right. And then finally, this last problem is going from it's going from molecules. So clearly we're talking about molecules because we have this huge number of them. Molecules to mass. So using our concept chart, we're starting with molecules and we're going to mass, but we have to go to moles first and then go to mass. So we're going to use both conversions. So let's try that. We're going to start with 7.53, and I'll do times 10 to the 25th power. And this is molecules of water, so molecules of H2O. And then I'm going to set up Avogadro's number first. So there's this many molecules in 1 mole of molecules. So, and then the next step, so that part takes me to here using Avogadro's number, and now I'm going to go molar mass to grams. So 1 mole of H2O is 18.02 grams. I just added up H2O from the periodic table as the atomic masses. And there we go. Okay, so now I'm using my cell phone right now, but I do have a scientific calculator which can handle these exponents. But if you are also stuck in a situation where you just have your cell phone, you might want to simplify this. So e to the 25 and e to the 23, that simplifies to e to the 2, 25 minus 23. So that's a factor of 100. 1 times 10 to the 2 is 100. So this times 100 times 18.02. Let's do it. Also, 7.53 times 100 is like moving the decimal point 2 places to the right. So I'm just going to type 753 times 18.02. And I get a huge number, 13,569. So I'm going to round this to 3 sig figs, so 13.6. And I'm going to put it in scientific notation. Times 10 to the 1, 2, 3, 4. Okay, and then always put your unit. What is this number? This is the mass in grams. Here it is, grams of water. So that's how many grams of water I would have for this many molecules of water.